Welcome to heat transfer. In this short video we're going to be deriving the heat diffusion equation, one of the most important physical equations of conduction heat transfer. Recall from the material that you reviewed this slide here that showed and introduced the heat diffusion equation. That's what we're going to be deriving, and for that we're going to be using the two tools we introduced before, Fourier's law and the first law of thermodynamics, and here's our equation again. And to do that, we're going to apply those two laws to a small sample element, a differential element. Think of it as a solid, doesn't matter. Cartesian, three directions, x, y, and z. Okay, so once again, so two tools. Fourier's law first, and number two, the energy conservation rate equation, or the first law of thermodynamics, in the form that we left off with in the previous video. Now, let's review some, let me finish this off here. Let's review some of the terminology that we're going to be using with these two tools. So in the first law of thermodynamics, we talk about M, that's the mass of the element in question. Then there's the specific heat capacity of the element, that's C, that's in joules per kilogram K. The density, the thermal conductivity, the prime physical properties for conduction analysis, let's box it up, that's in watts per meter K. And a new one, the thermal diffusivity, which is a property that's a combination of other properties, K over rho Cp, thermal diffusivity over density times specific heat. Let's box that one up too. Its units, by the way, dimension is meters squared per second. For the heat transfer rate, let me add the little subscript right there by the parenthesis. Note that that's the heat transfer rate by conduction only, and the subscript is going to break down the direction of the actual heat transfer. So it's the magnitude of the heat transfer flux vector. Again, that's a vector because there's a magnitude and a direction. So the Q sub x, for example, is the magnitude of the heat transfer rate in the x direction. Okay, so let's apply our two tools to this element that we talked about a little earlier. Okay, I'm going to call this figure 1, and got heat transfer again in the three directions here, which I'm highlighting for you right here. So heat in is Qx in the x direction, for example, and out is Qx plus dx. Okay? All right, so let's apply our first law of thermodynamics, equation 2, to this small differential element. So we've got the net heat in, so that's going to be Q sub x minus Q sub x plus dx. And in the y direction, it's going to be the same thing, y minus y plus dy, z, etc. Plus the heat generated within the element. Now that could be like a chemical reaction or electrical current flowing through the element. It's going to be equal to Q dot times the volume. All that's got to be equal to change in stored energy rate. Okay, that's from first law, that's mc dt dt. Substituting for m the density and the volume, we've got a new equation. So putting it all together and simplifying it, for the case of conduction in the x direction only, we've got this equation here. I'm going to call that equation 1. That's the main equation. So our goal here is to get rid of the q's. Okay, we don't a priori necessarily know what the q's are. We want an expression that expresses all this in terms of temperature only. So the first thing we're going to do is get rid of the Q sub x plus dx, or actually express the whole Qx minus Q sub x plus dx by doing a Taylor expansion on Q sub x plus dx specifically. So remember how that works, Q sub x plus dx, right? So if I know the property, the value of a function at x, then I can express it in terms of linear combinations of derivatives of that function with respect to x in the following form. And if my element is small enough in the x direction, then I can typically get rid of the higher order terms and simply look at the linear component of the Taylor expansion, which in this case would be the dqx dx times dx. Okay, so to a good approximation, if my element is small, Q sub x plus dx is equal to this. Okay, so keep that one in mind. We're going to substitute that back into equation 1. Once we've figured out what to do with Q sub x, and we're going to use our first tool, Fourier's law, in order to do that. Okay, so our next goal there is to express Q sub x itself in terms of temperature alone. Okay, we're going to start by looking at it in terms of the heat flux times, of course, the area in question. I'm calling that area A sub x. A sub x is based on the small element that we have, simply dy times dz, and you can generalize for a sub y and a sub z in the same way, right? Okay, so I've got a nice expression in the x direction for q sub x in terms of temperature now. I'm going to call that equation 2. Okay, going back to our element, let V be its volume. So since it's a differential element, that means dV. So that's dx, dy, dz. So using that plus the above result there from the first law and plugging that back into equation 1, we've got the following. Okay, don't forget that the energy generation term can be expressed as Q dot times V, and that simplifies. Let's write that down. That simplifies based on our volume, differential volume element as this. Okay. All right, so that now I can express the whole equation 1 in terms of the differential lengths that I have. I think you see where this is going. I'm going to get rid of these differential length here and end up with an expression in Q's only. And I know what to do with Q because I've came up with my equation 2 here from Fourier's law. Okay. There we go. Now it's time to substitute Fourier's law, equation 2, in there. I'm going to get rid of that Q sub x. Can't do anything with Q dot because that's a heat generation term. So that's going to have to stay with us for a while. But I've got a nice simple form, though, for the rate of change of temperature in the x direction if I only have heat transfer in the x direction. And so that's a sort of a simplified form of the heat diffusion equation, which we can generalize in the other two directions by lumping in the y and z components that I think follow naturally from what we did above. And we end up with the general form of the heat diffusion equation, the HDE. That was our goal. That was the equation on the slide at the beginning of all this. And we're done. We've got it. Woohoo! Heat diffusion equation. The first part of that, the derivatives in the x, y, and z directions, represent a neat conduction heat transfer into our element. The Q dot term represents the heat generation term in the element, right? And the right-hand side, of course, represents the net rate of change of the stored energy in the element. That's the heat diffusion equation. Commit that to memory. Very important. All right, so let's look at some special cases here, because in real life we are often able to apply it in easier cases where things become simpler. The first thing to do is to look at what happens if the properties don't change within the body. So that's thermal conductivity, density, specific heat, etc. They're all constant. So we can certainly pull the K out of the derivatives, and that makes the left-hand side much cleaner, right? So I've got this K that's out of the derivatives, and now I've got second derivatives of temperature all around. If you remember the definition of the thermal diffusivity from above, then if we divide by K, we're going to have 1 over alpha on the right-hand side, right? Similarly, for the second derivatives, that's the del square operator, and del square is also called a Laplacian. So the Laplacian of temperature is what we've got there on the left-hand side. Okay, box done. What if, in addition to having constant properties, we're also dealing with steady state cases? That means there's no changes with respect to time, right? So the whole right-hand side is going to fall out, and if there's no heat generation, no Q dot term, we end up with a very simple form of the heat diffusion equation, a very simple form, but a very powerful one, and that is the Laplacian of the temperature is simply going to be 0. Okay, a lot of problems actually just follow that. If we have that same case, but say with heat transfer in the x direction only, then the Laplacian becomes even more simple. So we're going to be looking at cases where that's the case. Enjoy. Thank you.